Hello everyone, my name is Suren and in this video I am going to present my ELP 101 project. The topic of my project is application of operational amplifiers and in particular I will be covering digital to analog converter. So before moving on to the actual circuit, let us understand what is a digital and an analog signal. A signal can be understood as a variation of a quantity with time. In this case, that quantity will be the electric potential or voltage. If the values that the signal can take form a discrete set, the signal is called a digital signal. For example, a signal that can take only 0 volt and 1 volt as its value. If the values that the signal can take form a continuous set or an interval, then the signal is called an analog signal. For example, a signal that can take any value between 0 volt and 1 volt is an analog signal. So this is the basic circuit of a digital to analog converter. First, we try to find the output voltage VO in terms of the four input voltages, that is V1 to V4. So we can see that the potential at V is 0 since it is grounded. And in an op-amp, the two terminals are virtually shorted, that is they are at the same potential. So the potential at point A is also 0. So since the potential at point A is 0, we can see that the potential difference across the resistor R1 is just V1 and thus the current through the resistor R1 is V1 by R1. And similarly, the current through the resistors R2, R3 and R4 are V2 by R2, V3 by R3 and V4 by R4. So at this node A, which is the collection of all these points, we applied the Kirchhoff's current law. And the Kirchhoff current law states that the algebraic sum of all the currents that are entering or leaving a node is equal to 0. Or equivalently, we can see that the total current entering a node is equal to the total current leaving the node. So here the current that is leaving is the current through RF and we represent that as I. And the current that is entering is just the current through R1, R2, R3 and R4. So we substitute the values of those currents here and we get I is equals to V1 by R1 plus V2 by R2 plus V3 by R3 plus V4 by R4. So I have copied over the value of I from the previous slide and we know that the potential at point A is 0 because we have already discussed that the points A and B are virtually shorted. So since B is grounded, so the potential of A must also be 0. So the output voltage, that is VO, is equal to minus of RF times the current through RF. And the current through RF is given by this expression as we have already derived. So the output voltage is equals to this expression here. So to simplify the analysis of the circuit, we can assume that the digital signal has only 4 digits and is in binary form. The possible values of the input signal being 0 volt and 1 volt. And the input signal is V1, V2, V3, V4 and this 2 at the base represents that the signal is in binary form. So to convert it into decimal form or in base 10, we have to calculate 8V1 plus 4V2 plus 2V3 plus V4. The magnitude of the output signal in our circuit can be made equal to the right side of the above equation if we choose the resistances carefully. So this is the expression for the output voltage that we had already derived. To get its magnitude equal to 8V1 plus 4V2 plus 2V3 plus V4, we may take the following values of the resistances. So we can check that the coefficient of V1 is RF by R1 and with this value it is 8 over 1 which is 8 which matches our desired value. Similarly for V2 it's RF by R2 which is 8 over 2 which is 4 which matches the desired value. So we get the correct magnitude of the output if we take these set of resistances. And note that there are multiple possible sets of values. This is just one example. So for the given set of values of the resistances, we get the desired output. The output has an opposite sign, but this can be corrected in a variety of ways. Thus, the given circuit is capable of converting a given digital signal into an analog signal. With this, we reach the end of the presentation. Thank you.